I'm a hydrogeologist. My motto in life is think out of the box. My name, Marcel. My experience, groundwater and soil contaminations. I'm the creator of Geo RGB, a channel of geographic information systems, GIS, geology, hydrogeology, and contamination. The purpose, the objective, the goal, the intention, the target, the desire. Share my experience and acknowledge to create points of discussion. The Geo RGB community. Promote the use of free and open source software. A free digital society. Provide technical advice to environmental companies. An opportunity for professional growth.
Hello guys and welcome back to my channel. In this occasion I'm presenting the Geostatistical Analysis course related to the creation of groundwater flow maps with Kriging Interpolation. We are going to be working with R and Rstudio for the geostatistical analysis and graph design, and with QGIS for the final map edition. We are going to compare the results we get with the geostatistical analysis extension of ArcGIS to see how we can get the same results. However, ArcGIS is a private software, but Rstudio and QuantumGIS are open source and free software. I am going to create a series of video tutorials where you are going to learn how to create a Kriging interpolation successfully. Unfortunately, Kriging interpolation is a kind of black box where most of the people just press the button next without understanding what is the math behind the Kriging method. However, in R, there is no button for next. In these tutorials, I am going to explain with examples, step by step, the spatial analysis methodology, where I am going to be talking about exploratory data analysis, experimental semivariogram, modeled semivariogram, cross-validation, Kriging interpolation, and also, at the end, we are going to be working with the map edition with QuantumGIS and also reporting results. This is the 11th video of the Geostatistical Analysis course and is going to be the last video for this course. The main topic for today is the map edition, but also we are going to talk about reporting results. We are going to see what is the model we are going to take to make the groundwater flow map. We are going to be talking about the map composition and also what is the relation between the contour lines and the groundwater flow line directions. To do that one, I'm going to introduce the concept of isotropic, anisotropic, homogeneous and heterogeneous aquifer. At the same time, we are going to make the interpretation of the contour lines and how we can work with the print layout to make a nice composition. At the end, I am going to compile the results from Rstudio to create a good technical report. Let's go to do it. At the previous video, we saw a very short introduction about the three main Kriging models: ordinary, simple, and universal. I also recommend 3 YouTube video channels specialized in this topic, just in case if someone wants to go deeper on the understanding of Kriging interpolation. Then we calculated the spherical model for a directional semivariogram of 135 degrees using ArcMap. Later, we were working with QuantumGIS to edit the raster files from Rstudio and ArcMap. At the end, we created 3 different map compositions to compare the results, one with the raster files, other with a mix of raster files and vectorial files, and the last one just with vectorial files. Remember that if you missed that video, you can hit the card located at the top right corner of your screen. Let's go to start the video of today deciding what is going to be the model that I am going to use to create the groundwater flow map direction. As I said the other day, for me the best model is the Gaussian one related with ArcMap, because the contour lines in this model are pretty smooth and they look very natural. If you compare with the other models where we have this kind of shape for this contour line and also over here this kind of shape, they look pretty unnatural, right? That is going to be pretty difficult to justify this kind of contour lines. Even for the Rstudio, the shape of this contour line, it's pretty unnatural. For these three models, I'm not going to talk about the Gaussian one because this model is pretty unnatural and it is not realistic. Then that one I'm going to remove. Then at the end, I'm not going to take any of the models from ArcMap because, as you know, ArcMap it's a private software and you have to pay a license to use it. However, Rstudio it's a open source and free software, and you can install the software in your computer for free and you don't need to pay anything. And as I like to promote the use of geographic information systems for free, I'm going to take a model from Rstudio. Even the Gaussian model for me it's the best. We even couldn't reproduce the result with Rstudio. And then it's another reason because I'm not going to take this one, right? But the main reason is related with the price of the license. Then all these models are going to be removed. And then we have to decide what of these three models we are going to use. As these three models are pretty similar, the differences are very tiny. The only criteria I'm going to use is the one related with the root mean square error. As this one is the one with the minimum error, I'm going to take the exponential one to create the groundwater flow map direction. That's the reasons, and let's go to create the map. I have my session already open in Quantum GIS with the raster image of the exponential model for Rstudio. And also I have the contour lines for the same model. Remember that we was working cutting this raster image at the previous video, and also we extract the contour lines for each of these models. The contour lines from Rstudio are really good, as you can see, these ones. For example, for the spherical one, also for this one. But the contour lines from ArcMap, the ones we extracted, are not really good. For example, let's go to see the spherical one. As you can see, we have a saw effect, and that is related with the pixels. I'm going to put here the raster image for the spherical one, this one. I'm going to put this one on the top. As you can see, there are 2 max pixels over there, and then we have the saw effect. I remember that at the previous video I told you that I'm going to show you a tool that you can use to make these contour lines more smooth. Then what we are going to do is just go processing toolbox, and it's going to be an algorithm for grass. Then you can share here generalize. Is this algorithm over here? Double click, then select the vectorial layer. In this case, it's going to be the spherical one from ArcMap. Spherical one, this one, and here you have a lot of parameters that you can change. For example, for this one, we are going to choose snakes. But you can play with all these parameters to get the best result. I'm going to leave all these ones by default, but you have to try different values to improve the contour lines. Then run, then close, and it's this contour line over here. As you can see, let's go to make this one a little bit thicker. and that's the original one, and the green is the one we created. As you can see, the contour lines improve a lot, removing all these angles from the contour lines, and it's a really good tool to use. If you make a big zoom, you are going to see also this kind of effect, but if you change the scale, you're going to see that the contour line is more smooth if we compare with the other one. But as I said, if you play with the parameters, you can improve the contour line. Okay, now let's go to use this one, and this one, and I'm going to remove all the rest from this one to this one. Remove layers. Okay. Now let's go to label these layers properly. This one is going to be the monitoring wells, and this one is going to be the groundwater contour in meters. Then click here, rename the layer. It is important to label these ones properly because we are going to use these names for the legend. Then what I'm going to do now is take this one out and bring here the satellite image that is going to be from Google satellite. Is this one, and as we have the layers georeference already, the satellite image is directly located properly. This is our area. Remember that when we are using this plugin, this one here, Quick Map Services, we are taking the satellite image from a server. Then we need internet connection. If your work area is so big, maybe it takes time to load all the image. Then if you want to avoid this situation, you can download the satellite image directly. I have a video tutorial, this one, the how to download Google Earth high resolution images with Quantum GIS. I'm going to leave the link here at the top right corner of your screen, where I explain step by step how you can get Google Earth high resolution satellite images using this plugin. Also in that video you can see how to install this plugin in Quantum GIS. Then once you have the image downloaded, you don't need internet connection to use that image. Now what I'm going to do is edit these contour lines. I'm going to change the color because purple it's not good for groundwater. It's going to be this kind of blue. Apply. Let me see. I'm going to close this one here, and I'm going to save the project. I'm going to add the labels now. Then properties, labels, single label. Here we have the elevation, and then we have to select the parameter we want. We want a buffer. It's okay. And let's see the placement. We want horizontal, no, parallel, and on the line. Apply. Okay, but let's go to make the numbers bigger, and also in a blue color, bold, and it's going to be not this one, this one over here. Apply. Okay, that one looks good. As you can see, each contour line is 0.5 meters. But looks like the buffer let me choose this one, apply. Okay, now it looks better. And also for the monitoring wells, let's go to choose a different symbology. Symbology here, and we have all these options. We can take this one, for example, and blue color. Let's see how it looks like. And also let's go to add the number of the piezometers with the labels. Here in this case, piezometers, apply, and let's go to make the numbers smaller. 8, for example. At the moment I'm going to leave these labels like that, but maybe at the print composition we are going to make some change just to have the better way to show the data. Other important thing on the map is the background we are going to use. In this case, the only option we have is the satellite image for the background. But if we leave the image like that, we are not going to see well the information related with the groundwater flow map. Then what we can do is make here a transparency for this map. Transparency here around 40%. Apply. And in this case we can see well the groundwater flow map, and we can see also the background. We can see the roads, the gas station, the river. For the groundwater flow maps, I like to use the CAD drawing for the facilities at the site, but in this case I don't have that information. Then if you want to digitalize all the facilities and the roads and the river, I have a video where you can learn how to do that one using just Quantum GIS. Is this video. Quantum GIS CAD tools for editing, and in this case what I did is from a satellite image I created the facility map in a CAD using just Quantum GIS. Then if you want to watch that video, I'm going to leave the link at the top right corner of your screen. The background in a map of groundwater flow map direction is really important, and sometimes even the background can provide information related with the shape of the contour lines. It is very important to make a map that it's not crowded of information. I mean, for example, for the background, if you are going to add the CAD of the facility, don't add the labels for the name of the facilities, or even don't add the name of the roads, because that's an extra information that it's not related with the groundwater flow map direction. When you are doing a map of the groundwater flow map direction, what you want to present in that map is the information related with the groundwater, exclusively with the groundwater. The goal is to show a map where the information is concise and very clear, and with a glance you can make an interpretation of that information. That's the goal of the map. Now let's go to create the groundwater flow direction lines. To do that one, just go layer, create layer, new shapefile layer, then select where you want to save the file. It's going to be a shapefile, and flux lines is going to be the name, and this one it's okay, but for this one is going to be line. This one is going to be this one here, okay. For the rest of parameters is okay. Then press this button to edit and select this option over here. Then go here, and we are going to make lines that are going to be perpendicular to the contour lines. And then this one, for example, like this one. Then this one is going to be number 1. Then other one, for example, from here to here. Number 2. How many groundwater flow direction lines I'm going to make? Well, you know, enough to make an interpretation of the contour lines. There is no any specific number. I make a total of 9, and I believe that is good enough. Then I'm going to edit these ones, close here the edition, save, and I'm going to edit these lines. Here for the color, I'm going to add a blue color, and here I'm going to add an arrow. this one and let's see, apply. And we can edit these arrows. Then go here, select this one, and I'm going to add 0.5 and 0.5. Apply. Something like that is good. At this point, I would like to clarify something really important related with the groundwater flow direction lines. As you can see, I place these lines perpendicular to the contour lines. Then when we are doing something like that, we are assuming that the aquifer is homogeneous and isotropic. What it means. Let's go to see this slide here. Isotropic. Isotropic is when we have the same hydraulic properties in all directions. Then the anisotropic, what we have is the different hydraulic properties depending on the direction. It means here that if we, for example, talk about the hydraulic conductivity represented by the letter K, then we can say that we have the same value for the hydraulic conductivity at the Y direction, at the X direction, and all directions inside this circle. Even we can think in a three-dimensional if we have the zeta axis. And the opposite for the anisotropy. What happened here, the value for the hydraulic conductivity is smaller at the Y direction compared with the value that we have at the X direction. Other important concept is related with the homogeneity. For example, we have an aquifer that is going to be homogeneous when we have the same hydraulic properties in all locations at the aquifer. In this case, as you can see, we have, for example, one well here and one well here, and they present the same hydraulic properties in both locations. The opposite is this word that for me it's really complex to pronounce in English, but I'm going to try. Helterogenerity. We have different hydraulic properties depending on the location of the aquifer. For example, in this case, we have an aquifer that's heterogeneous, and what happened, we have one well here and also one well here, but as you can see in both locations, the hydraulic conductivity is changing also in the Y direction and also at the X direction in both cases. Then at the total, we can have 4 different X scenarios represented by these 4 graphs over here. Then we have homogeneous isotropic, homogeneous anisotropic, heterogeneous isotropic, and heterogeneous anisotropic. Then in most of the cases, when people make the maps, they make an interpretation like this one, where they are assuming that the aquifer is homogeneous and isotropic to simplify the results. But it never happens, you know. If you want to assume a realistic X scenario, all the aquifers are going to be anisotropic. You know, it's going to be a very exceptional aquifer where you have the same values for the hydraulic properties. However, to calculate what is the real direction of the groundwater flow, it is very expensive because you have to do a lot of hydraulic tests to know what is the hydraulic conductivity in all directions at the aquifer. And I'm going to explain a little bit how to calculate. Then let's go to open this one. Then let's go to assume that we have, for example, something like that, and the directions for the hydraulic conductivity is going to be this direction. I'm going to change the color for a lilac, for example. This is the major axis, and this one is the minor axis. And then, for example, let's go to suppose that we have the contour line that is doing something like that, for example. Let's go to change the color. And here at the center, what we have is the piezometer, right? This is over here, and that's our piezometer. Let me fill this one with blue. Then what we have to do, it's a perpendicular line to the contour line from the center of the ellipsoid. Then it's going to be, for example, something like that. That's the perpendicular line to the contour line. Okay, I'm going to change the color for this kind of red or brown. Then where we have the intersection of this line with the ellipsoid, then we have to place here a line that is tangent to the ellipsoid. Then it's going to make this line, for example, assuming that this line is tangent to the ellipsoid in that point. And I'm going to change the color for a green one. And the last one is going to be a line. Okay, let me change this one. It's going to be a line that is perpendicular to this green line. Then a perpendicular line is going to be something like that, and it's going to be in this blue. And then we have to place this one at the origin, at the piezometer over there, and that's the real direction of the groundwater flow. Okay, something like that. Then, for example, in this case, at the beginning, if we are assuming that the aquifer is homogeneous and isotropic, we are going to have this direction. But if we are assuming that we have some anisotropy, we are going to have this direction. This explanation doesn't pretend to be a guideline about how to calculate the groundwater flow direction when the aquifer is anisotropic. It's just a very simple explanation that tries to introduce you to that concept. But if you have to calculate, I highly recommend to read any book to have a better understanding. Then if we have a map where the groundwater flow direction line it's not perpendicular to the groundwater contour, like in this case, we have to assume that someone calculated the anisotropy of the hydraulic conductivity, and the direction that is shown by the groundwater flow direction line is the real direction of the groundwater flow. When the groundwater flow direction line is perpendicular to the groundwater contour, like this green line, what we have is that the angle between the groundwater contour and the groundwater flow direction line it's 90 degrees. And for this option we have two different scenarios. One, the hydraulic conductivity was calculated and it was the same in all directions, and then the groundwater flow direction line it's perpendicular to the contour line. And the other scenario is the hydraulic conductivity was not calculated, and the person who is doing the groundwater flow direction map is assuming that the aquifer is homogeneous and isotropic, just to simplify the results of the groundwater flow map. Unfortunately, I have to say that I saw a lot of groundwater flow maps where the groundwater flow direction line it's not perpendicular to the contour line, and the reason it's not because they calculate the anisotropy of the hydraulic conductivity and they place the arrow for the groundwater flow direction line according to the flow direction. The reason is because some people don't understand what is the relation between the groundwater contour and the groundwater flow direction line. And that's a very big issue, because if you are dealing with a contaminated groundwater, you want to know what is the groundwater flow direction. just to understand what is the migration, what is the movement of the contaminant, and what could be the potential receptors. Then the groundwater flow directional lines are really important and has to be something very clear at the groundwater flow map. Let's go to move to the next thing. I am going to change the name of this one for groundwater flow direction line. And now let's go to start with the composition. Just press this option here, then select a name. I'm going to put number 3. Okay. Now click right on your mouse to choose the properties of the page. In this case, the size is going to be a letter. In this case, I'm going to load a template I created already. Add item from template. And it's this template. What I am going to use from this template is going to be this couple of boxes. Then for the other maps, I'm going to remove all these ones. Just go here, select the things you want to remove. It's going to be the maps, this one. You have to unlock, and this one also is going to be removed. Then delete and delete. And then what I'm going to do is change the orientation for this one. And I'm going to organize these ones a little bit. I'm going to move all these ones to here. And I'm going to take this one out at the moment. Maybe later I'm going to use. Maybe it's locked. Okay, and I'm going to save this one. If you want to learn how I created this box, you can check the video tutorial I have in my channel. Is this video tutorial, how to create a map using QuantumGIS for beginners. I'm going to leave a link at the top right corner of your screen. In this video, you are going to see step by step how to create this box and also other things related with the composition of a map. Now I'm going to create a frame for the map, but I'm going to move these ones a little bit over here. Then I'm going to create a rectangle, and I'm going to place over here. And I'm going to make this rectangle transparent. And I'm going to lock the rectangle also. Is this one? No. This one here, as you can see, it's black. I'm going to lock this one, and I'm going to remove the north, and I'm going to move these ones. Something like that. Now I'm going to load the map with this option here, add a new map to the layout, something like that, and I'm going to add a scale here, 2500. Then with this option here, you can adjust inside the map. Going to make this one bigger, then go outside. But first I'm going to add the UTM coordinates. Then to add the UTM coordinates, go here to grid, plus, select, modify, select the interval, for example 50 meters. Let's go to see how it looks like. Maybe 100 meters, it's going to be better, too much lines. Then it means each square of this map, it's 100 meters by 100 meters. Let's go to edit the kind of line we want. I want something like this one, dash line, and the color I want something very discreet, like this one. Now go back with this option here, and now let's go to choose the frame. I want interior and exterior ticks. Go down, and I want to see the coordinates, but I'm going to change the orientation. For the left, I'm going to go to this option and I'm going to put vertical descending, and for the right the same, vertical descending. I'm going to remove the decimals. I don't want decimals. To 0. And I'm going to change the font to see the numbers properly. Then go here for bold, maybe number 9, okay. And now you can see the coordinates better. Or maybe smaller, number 8, okay. That one looks good. And now we are in conditions to adapt this one to the frame, the outside frame. That's too big. Maybe something like that. Okay. And now we can adjust the image inside. Then go here, select this one, back, go to the scale again, 2500 for the scale, maybe 2000, let's see how it looks like. Okay, 2000 is too much, 2500, looks good, you can see everything. Let me check. The information is not very crowded. You can see the roads, the gas station, the river, the number of the piezometers, the contour lines, the piezometers. That's good. Now let's go to fix the scale, this scale. I'm going to remove this one here. And for this one, let's go to see here, what is this one? This scale over here. Yes, select this one, and here select the map. It's going to be for map 1. And then we have to select the units and all other parameters. Go here to segment, and here we can put maybe 50 to have something from 0 to 100 meters, and that's the same distance as from here to here, because as we place the UTM coordinates with a difference of 100 meters. It is redundant to put the bar scale because you have also the distance here, but I like to add it. The coordinate reference system is a good one, but here I have to change the name of this map, and it's going to be groundwater flow map. Here, select over here, and then we can change the name. Make this one bigger. Okay. Now I'm going to add the legend. Just click this option here, add a new legend to the layout, select the area where you want the legend. It's going to be over here, and then click select this option here, and then take this one out, and then you can edit the things you are going to add at the legend. Then I'm going to select this one. I don't want this one. I'm going to remove, just selecting this option here. And that's it. Also, you can select the font and the other parameters with this option here, each into the font, and I'm going to change here for a number 10 and bold. Okay, that's okay. And now what I'm going to do is add a label that is going to say lesson over here. Okay, and lesson. That's good. I'm going to change the font for a 12 and bold. Okay, maybe bigger, 12, 14. Okay, something like that is good. We're going to add this one a little bit. Okay, and now I'm going to add a rectangle. And I'm going to make this rectangle transparent. And I want this one and this one to be the same height. Then I'm going to move this one a little bit. Rectangle, this one. Go down a little bit. Something like that is good. I'm going to save. And I'm thinking to change the scale. Then I'm going to go to the map, this map here. I'm going to try to make this one 2000. In this case, what we have here at the map is 1 millimeter at the map is 2000 millimeters on the reality. It means that 1 millimeter on the map is 2 meters at the reality. Then in order to adjust this one, I'm going to make this one bigger, and also bigger from here, and also bigger from here. And I'm going to try to adjust inside. This one 2000. It's pretty tight for these two piezometers over here. Then I cannot see the ones over here. Okay, then has to be 2500. I like to put numbers like that because in that way it's easy to read the information on the map, because as you know, if you put 2500, it means that 1 millimeter on the map is 2.5 meters on the reality. But if I put something like 2100, it means that 1 millimeter on the map is 2.1 meters on the reality, and that's quite weird. Then I prefer to pass from 2000 to 2500. Now I'm going to add some notes here related with this map. I'm going to take this box, I'm going to place over here, I'm going to make this one the same as this one here. We can add some guidelines, for example this one, let me see, this one here, and also this one here, this one is good, this one can be a little bit more here, and also I'm going to add one here, and I'm going to move this one here. Okay, something like that. I'm going to take the notes here, and I'm going to move over here. Then I'm going to add the date of the satellite image. I believe that it's very important, and you can check here at the Google Earth. As you know, the satellite image that we are using is this one. If you take the transparency 100% here, you are going to see that this image is the same as the one we get here at the Google Earth. Let's go to look for our site. This is the site. As you can see, this image is the same as the one we have here. Then in Google Earth, you have this option here that you can click at the bottom, and you have all these dates here. Then if you move to 2000, okay, if we take this one out and you may zoom, you are going to see here what is the imagery date, as you can see here. That is from July 9th, 2016. But also if you click here, you can change the imageries they have in Google Earth. And if we go to that date, you are going to see that is the same image, is that day here, July 9th, 2016. And that's the date we are going to add here at the map. Then let's go back to the transparency. 440, apply, close, and that's the information I'm going to add here, but I'm going to pass the video faster. At the end, I decided to add these two notes. One, it's related with the date of the satellite image. That is very important because if we are doing this map in 2020, and the imagery is from 2016, maybe now we don't have this landscape. Maybe it changed. Maybe even the gas station is not here and the roads are different. And it is very important to indicate on the map the date of the satellite image, because the X scenario can be totally different, right? And also I added a note related with the groundwater contours. As you can see, groundwater contours extracted from an exponential model of an omnidirectional semivariogram using Universal Kriging, Appendix 2. That is, I am going to compile the information from the Rstudio. I'm going to show you now how to do it, and we can add that information on the report in Appendix 2, for example. It is important to indicate this one because in this map, we are not going to add the groundwater elevation at the piezometers, because the groundwater elevation that we have at the model, it's not the same as the groundwater elevation we have at the reality, as we saw when we was doing the cross-validation of our model. Then it doesn't make any sense to add here the real groundwater elevation, because maybe it's going to be a discrepancy between the values that we show at the piezometers with the contour lines. In order to avoid this kind of confusion, I decided just to add the values for the contour lines, but not the real values for the piezometers. Now I would like to talk a little bit about this contour line, the one for the 95 meters. Let's go to the map. And as you can see, this contour line, the shape, it's pretty weird. Also this shape over here, but I'm going to talk about this one, and I'm going to try to make an interpretation of this contour line. Then if we measure the distance with this tool here and we add here meters, we are going to see that the difference from this contour line to this contour line is half meter, and the distance it's approximately 15 meters more or less, and the distance from here to here it's more or less 5 meters to the base of this contour line. Then the relation between, okay, I'm going to copy this image, it's going to be easy to explain. Okay, as we said, from here to here it is 15 meters, and from here that we are going to follow this contour line over here more or less. Then from here to here it's more or less 5 meters. then the relation between this one and this one is 1 divided by 3. Then if we make this with a calculator, it's 0.5. That is the distance between this contour line and this contour line, divided by 3. That is the relation between 15 and 5, and equal. That it means that this contour line over here with this shape, it's elevated 0.16 meters from here to here, and from here to here is 0.5 meters, as we saw here, the difference of the contour lines. But from here to here, the groundwater is elevating 0.16 meters. That it means is 16 centimeters. Then also we can measure the distance from here to here. Let's see what happened. The distance from here to here, it's almost 20 meters, as you can see there, almost 20 meters close. Then I created this graph, and as we said, the distance from here to here, it's approximately, that's a very bad line, going to take this one, from here to here, 20 meters. And from here, I'm going to take one more line, and from here to here, we say that that one is 0.16 meters. Okay, the relation is not really good. The scale, that has to be longer, or that one has to be short, right? But the point is, when we make this interpretation, we have to think that if we take a section over here of this contour line, what we are going to see is something like that. And the question is how we can justify that we have this kind of peak at the groundwater elevation, right? This is the groundwater elevations. It's go down, right, according to the gravity. And if you have something like that, you need energy to go up with the water, right? Or maybe there is another explanation, because here at this area, maybe it's a point where the aquifer is recharged, or maybe it's a point, maybe in this piezometer we are injecting water, and that's the reason because we have this kind of shape, right? But if you cannot justify this kind of things, like this one, that it's pretty unrealistic, right? And you don't want to have contour lines like that. But what we know is we make a model, and that model try to make an interpretation of the reality, but it's not the reality, it's just a model. Then what happens when we have this kind of contour lines? Well, we have different options. One of the options is take this contour line, click here to the edition, select this contour line, all these points over here, and remove these ones. And that's the contour line. And that's your interpretation, right? And I believe that it's even not wrong, but maybe some people is not going to be agree with me. But you know that contour line is not realistic, and you can remove it if you want to make that interpretation. But then you have to explain on the report and also maybe on the map that you modify this contour line to have a better approach to the reality, right? We are not going to do that one. Then so here, save, no, discard, and we keep the same contour line. It is also possible to edit this contour line to make this shape less exaggerated. Then press this button here, select this option, and then try to make a contour line that is a little bit less exaggerated. For example, something like that. That it's just an approximation. And then put here the elevation that it's 95. And then remove the contour line that you don't want to have. For example, let me open this one. 95. Is this one here? Then you can take this one and leave the other one, the one we created. As you can see now, it's less exaggerated. But we are not going to do also this one. Then close this one and discard, just to keep the same as before. Other option is to do all the Kriging interpolation and remove this wall from your data, because maybe the groundwater elevation in this well was measured in a wrong way, or there is something wrong on the measurement and it's not right, and that's the reason because you have this contour line. And the last option is leave it like that. Most of the people is going to do that one, and because we know it's a model, and a model it's not the reality. And then who has the last word is the professional, the person who is doing the interpretation of these contour lines. Okay, now let's go to work with this one. I'm going to add the north arrow here. That's also really important. Just click this option here and select an area on your map where you want to place the north. Then go here and select the one you want. Also here there are different options. I'm going to leave this one, but I'm going to make this one smaller, something like that. And now I'm going to export the map as an image first. Close. Going to save as a number 3. As you can see, the quality of the map is really good. You can see all the information properly. Piezometers, contour lines, and groundwater flow direction lines. Also, you can see really well the background, the roads, the gas station, the river, and also all the information related with the box, the scale, the coordinates, the nodes, the legend. Okay, and now I'm going to do the same, but now I'm going to export as a PDF. Close. Number 3 is good. Save. And that's the final report for the map. As you can see, the PDF also has a really high quality. The last thing we are going to see today is how to create a report from Rstudio. Then what I'm going to do is just copy some of the scripts we was using and some maps, for example, until here. Copy, and I'm going to open a new one. And I'm going to paste here. I'm going to add a script. And I'm going to paste here. There is a very professional way to do that one with this option here with Markdown. There is a lot of videos in YouTube that you can check to create a report with this option. What I'm going to do is just compile with this icon over here, compile the report. When you click over here, the software first is going to ask you where do you want to save the file, and then it's going to appear this screen. Then here you can select what format do you want for the report. I'm going to select the Word one and then press the button compile. When the process is finished, is going to appear a word, and then you can edit this work. For example, I'm going to change the size of the letters for a size of 8, for example, and also you can change here the titles. You can edit that one as a regular Word document. Also the graphs, you can change the dimensions, for example for 35, and that's it. That's pretty simple and very easy to use. If you use the other option, this option over here, it's a little bit more complex and it takes more time but looks more professional. But this option is also a good resource and very easy to manage. Now I'm going to show you the report I created. Is this one here, and as you can see, I added here at the top Appendix 2, Universal Kriging Groundwater Flow Analysis, and here we have all the steps we did to create our model with all the information. And it is very important to add this kind of documents in your report, because it gives very good credibility to the information you are presenting in your report, and it makes the difference between a good report and an excellent report. An excellent report for me is that report that you can take the data from the report and reproduce the same results. There are a lot of companies that they don't put all the data they are using to create their report, and for me that kind of reports lose some credibility, right? Because you cannot reproduce that results. And for me it's very important to add all the information that you was using to create that results. Then if other people is reviewing that report and they want to reproduce the same results, they can do it because they have the information in the report. And that's the way a company can gain very good reputation for the technical reports. Okay guys, that's the end of this video. Thank you very much for watching, and see you on the next one.